Hey everyone, welcome to step 5 of the scientific method. Here we're going to learn a little bit more about how to analyze the data that we've collected and draw some conclusions. So, just to recap, we first started by asking a question and making observations about the world around us. Then we completed some ethical background research using a variety of different sources. Then we constructed a hypothesis, tested with an experiment. One thing I'd like to point out here too, here in the middle, if for some reason we find that our procedure is not working, it's time for us to go back and rewrite our procedure and our experiment to a point where it can be done efficiently. I didn't mention that in the previous video, but there you go. So we've collected our data, our procedure is running smoothly, everything is good. It's time for us to look at that data and start to analyze and draw some conclusions. Okay. So if we were in class, we'd have a nice little discussion right now about the importance of presenting data ethically and how it can be presented effectively. The main thing that guides the discussion is this graph over on the right. Okay, so I want you to hit pause and kind of compare and contrast the two graphs. Okay, so what are some things that we notice? Over on the left-hand side, we know that the gap between 2007 and 2008 is pretty big, right? It looks like a significantly bigger gap than the second graph over here. The reason why is because of our x-axis, or excuse me, the y-axis. So technically, when we are creating a graph, I would like us to either, number one, if we choose to do something like this, include what's called a break over here. That signifies we jump from 0 to 85, or do what's done on the right-hand side and start at 0 and go all the way up to 100 and up by 20 by consistent and uniform days of freezing temperatures. Okay, because in reality, in 2007, we have 82 days of freezing temperatures, and in 2008, we have 84 days. That's not a hugely significant big difference on the graph. It shouldn't be. Similarly, on the second graph over here, it's very small difference, but it's portraying the same exact data. So it's important that we create our graphs to make sure that they are representing our data in the most correct and accurate manner. Because if we saw a graph like that on the left, on the front of a magazine, and we didn't really pay attention to the axis, like many of you probably don't, nothing wrong with that. I'm a fast reader myself. But we want to make sure that in our research experiments, we're presenting our data with as much integrity and clarity as possible. Okay, so if you do want to do something that kind of shows the difference a little bit more clearly, include a break right between here to indicate that we jump from 0 to 81, or preferably stick with what's over on the right. Okay, so quantitative data and qualitative data are both types of data that can be utilized in an experiment. Many of you guys are probably going to be using data that is more quantitative. And quantitative data is most often presented in graphs or charts. I have a couple videos there that you can go ahead and watch if you're stuck on what type of graphs that you should use. There's a lot of different graphs out there that we know from math class. There's scatter plots, there's bar graphs, there's line graphs, there's pie charts. I'm a fan of pie charts myself just because they're kind of fun to look at. There's even donut graphs, which are basically just pie charts, but they look like donuts, which I think are pretty cool because I like donuts. And then the second form of data that we can use is qualitative data, and that can be presented simply as text or just words, okay? So it isn't very easily converted to graphs or charts generally. Sometimes it can be, but most of the time it's not. So in your experiment, you may collect some quantitative data and some qualitative data. Many of you are probably going to be simply using quantitative data though. Okay? So some tools that we can use to help analyze trends. There's a lot of them. Some of these are mean, median, mode, range, outliers, and correlation or R-squared value. Okay, so just to recap, mean is when we go ahead and we take all of the data that we collect and we find the average. And that's basically calculated by adding up each value and then dividing by the number of values that we've added together. So if we have, let's say, 3 data points in our experiment, we have 100, 150, and 200. To find the mean, we're going to go ahead and we're going to add 100 plus 150 plus 200, and that should give us, let's see, 450, and then we're going to divide that number by 3, and that's going to give us 150 for our mean. Okay, our median is simply the number in the middle when we arrange it from smallest to largest. So again, 100, 150, 200 Our middle number, our median, is 150, so that's our median. The mode is the number that appears most often in our data set. So if I were to throw in another 200 there, so it was 100, 150, 150, no, excuse me, 100, 150, 200, 200, our mode would be 200 because the most common number that's in the data set is 200. The range is simply the spread of the data. So if our smallest number is 100 and our largest is 200, our range would be 200 minus 100, which equals 100 for our range. Outliers is something that is either extremely high or extremely low. There's a specific formula that we can use to help calculate outliers. The statistical procedure, we're not going to get into that here unless you really want to, but an outlier is something that visually looks off on a graph. So let's say that we had our three traditional values of 100, 150, and 200, and then we got a value of 950 that came back. That's a really high number compared to our other three. That would be considered an outlier. Similarly to the graph over here, we'd see a nice little trend, but then we have that nice point over there that's saying, your theory is wrong, outlier, and you can erase that because it's an outlier. Something probably went wrong in collecting the data. So when we get closer to collecting data in our experiments and we have an outlier, be happy to help you out. We can discuss maybe removing that or maybe keeping it just for the heck of it. The last one is R squared value. And if you take one of the statistics classes, the hard word to say at school, you learn a little bit more about that. But when we have a line that is going the same direction, that's a line that's said to be very well correlated on a scatter plot. So right here, this is a pretty good correlated line. All of the points except for this one tend to follow the same kind of trend. Okay, that, my friends, is correlation. Now, correlation value of 1 or -1 means that it's very well correlated. But anything that's closer to 0, so like a correlation value of 0.1 or 0.2, that means that the data is just kind of all over the place and there isn't really a true correlation. And we can do a lot of statistical methods like hypothesis testing and things like that to figure out the R squared value and figure out if our data is truly correlated, but we're not going to get into that. So correlation is essentially how correlated or how closely related the data points are. We calculate that through what is known as a scatter plot. So using the data I provide you in your case study, I want you to go ahead and complete part 5, crunching the numbers. And when you're done, come on back and we'll finish out with part 6. Thanks, guys.